Welcome to Academic Digest class. Still on chapter 11, exercise 11, number 11. So a cork weighs 25 gram, and you know that cork, this is when you're talking about something that its density is less than that of water, so it tends to sink. So it weighs 25 gram. When a brass sinker weighing 85 gram is attached to it, the two just sink in water. If the relative density of brass is 85, what is the specific density or relative density is a specific gravity of the cork? So to answer this question, let's pull out the things we have. So let's say mass of cork 25 gram, mass of the sinker 85 gram, 85 gram. Or in most cases, we say that the density of brass cannot be 85 but 8.5. So cannot have a mass of 85 and still have density of. So it says the density of brass. So let's see, that brass is the sinker. So the density of the sinker is 8.5. What is the specific gravity? So okay, sorry, this is relative density, not just density. Yes, the relative density of this is 8.5. So relative density of the brass of the sinker, the relative density of the cork is what we don't know. So in order to find this question, to find this, the solution we use is always the solution that comes from total volume. This is a formula you need to know, equals to volume. Whenever you are given question on cork and sinker, think about this two, this formula. So volume of sinker plus volume of cork. And you need to know, remember that density first of all. Okay, you also need to note that whenever you have a floating body, or you hear sinker and cork, that mass is equals to the total mass is equals to the total volume. See how? We know that density, relative density is equals to density. Let me do it here. We know that relative density is equals to density of substance over density of water. And remember that the density of water is 1 gram. So this is equals to density of substance all over density of water, which is 1. Anything divided by 1 is that. So relative density is simply density of a substance is the same as mass over volume. So you can now see it, mass over volume. So which means that right here, yes, which means that if you want to make volume subject of the formula now, volume that is here will now be equals to volume equals to mass of that substance all over its relative density. Have you seen it? Yes. So if that be the case, you can now say that the mass, okay, let's try to apply it here. So let's try to apply it. If I want to get the volume of this sinker, let me get the volume of this sinker. To get the volume of the sinker will simply be mass given 85 gram of the sinker. The relative density is 8.5. So the volume of the sinker will simply be 85 gram all over 8.5, which is equals to 10. So since I'm using gram, it will be centimeter cube. So I've gotten it. So let me come and put it here. 10 centimeter cube. Now, for volume of cork, the volume of cork using the same formula, I know that volume of cork was not given. So V of cork equals to, but the mass of the cork was given 25 gram all over The relative density, that's what I'm looking for. I don't know it. So all over the relative density. So that means that the volume of the cork is simply 25 all over relative density. But total volume, what will be the total volume? Let's get the total volume. We know that the total volume here will simply be the same thing as saying 25 plus 85. So that is total mass equals to total volume. So if we do, when we compare this substance, if we do, let's compare the whole substance, and we say relative, let's say we do density now equals to mass over volume. Let's use this thing now. Let's compare the total substance. Since we are talking about total substance, let's say the total substance here is 85 plus 25. 85 plus 25 should be around 110. Yes, I'm correct. 110. All over. The volume I don't know. But notice that the total substance is simply talking about that cork and the sinker. And notice that everything that happened to it is inside, they are entering inside water. And as it enters inside water, it will tend to lose weight. When something enters water, it tends to be less, or it has more, or should I say, it has lesser weight. So if you check it, you now see that the density of what is entering inside, the mass, the density of what is entering inside is water, and density of water is 1. So this is 1 equals to 110 over volume. So if you check it now, you now see that this will be volume times 1 equals to 110. So this is why we say that whenever you hear water was displaced, or you hear a body that is floating is pulled in with sinker, without thinking too much, just consider that the total mass is equals to the total volume. So if I know this, I will now come and put that here. Total volume will be 110. Since everything is in gram, that means this one being centimeter cube as well, because we are dealing with something that is not in SI units. So if you check it, we now have 110 equals to 10 centimeter cube equals to 25 over RD. So let me put this out to another space so I can complete it. So I now have 110 equals to 10 plus 25 over relative density. Whichever way you do this, you end up doing 110 minus 10 equals to 25 over RD. So this is 100 equals to 25 over RD. This will cross multiply so that you have 100 relative density equals to 25. Divide both sides by 100, the coefficient of RD. So you see that RD will become, so let's do it, 25 divided by 100, 0.25, 0.25. And remember, relative density does not have units. So this is your answer for that number 1. Let's move to, yes, so what is the specific density of the cork? So this is the relative density of the cork, 0.25. There's no time. Let's move to this one. They said, why is it necessary for the stem of the hydrometer to be as small as possible? Okay, I know that it needs to stand upright and it needs to be able to float and to adjust so that you'll be able to see at eye level whatever you are getting as you're reading. I told you I'll be making a video on hydrometer, and please still remember that I said that hydrometer tends to go in deeper inside lesser dense liquids, and you only use it for liquids. Why? If it's very dense, it tends to float higher. So I'll still make video on that. So let's move to the question part. That is why we're here. They say the hydrometer of mass 0.12 kg, a uniform cross-sectional area 2.5 times 10 raised to the power minus 5 meters square is placed in a liquid of density 1.35 times 10 raised to the power 3 kilogram per meter cube. Calculate the depth of the hydrometer. You always need to know that depth is either it's talking about length or height whenever you see that depth. So first of all, the best way to answer this question is to always pull out the units or parameters. You see parameters given to you. So still on chapter 11, exercise 11, number 12 this time around. So to answer that question, all I need to do is to say, here I am given that the hydrometer mass of hydrometer equals to 0.12 kg. This area of hydrometer, 2.5 times 10 raised to the power minus 5 meters square. Then in a liquid, this liquid has a density, liquid density of 1.0 of 1.35 times 10 raised to the power 3 kilogram per meter cube. They're now asking us to find the H, the depth of the hydrometer. So what I will use, the formula I will use is simply the formula of P. I've proved this thing in the first video, equals to rho g h. And remember that this is pressure. Pressure is given by mg, force over area, mg over area equals to rho g h. So over 1. This can take care of this. So this is now m over a equals to rho h. Making h subject of the formula, this can come here. So I now have m over a rho equals to h. So now I can substitute. Let me substitute. So h will simply be 0.12 all over 2.5 times 10 raised to the power minus 5 times 1.35 times 10 raised to the power 3. So let's do this. First of all, multiply the denominator. So I do 2.5 times 10 raised to power minus 5 times 1.35 times 10 raised to power 3. So I have h equals to 0.12 all over 0.03. This can be 3.38 times 10 raised to power 2. Okay, but let's just write it the way it is. So now that I have this, I can now do 0.12 divided by 0.03375. So I now have h to be equals to 3.56 and is in meter. So that will be the depth. So the depth of the hydrometer will simply be 3.56. So we've noted that. So let's moving on. I've calculated the depth. Let's move to number 16. This is number 12. Number 16. There says state Archimedes principle. Number 16. This is the one we solved now. State Archimedes principle and use it to derive an expression for the resultant force experienced by an object of weight W and density P naught, initial density, when it is totally immersed in a liquid of density. First of all, let's state Archimedes principle. So Archimedes principle is simply the same thing as force, but we say that is what you call buoyant force. It's simply the force you find in a liquid. So it states that the force Archimedes, or you say Archimedes, whichever one however you want to pronounce it. So the principle states that the force experienced is like trying to tell you how you know that there is a force experienced by a liquid. So the force experienced by a liquid is equal, or you say directly proportional, is equal to the amount of liquid displaced. So it's the same thing as saying the force experienced by water or a fluid is equal to the amount of liquid or amount of fluid or amount of water displaced. So it's trying to tell you that if you put hand inside water, that water, if it's filled up, it will continue to leave the containing vessel until it's equal, the number that leave equal the amount of mass or amount of or the weight of your hand that you put inside. So that is what that law is trying to talk about. So it's simply saying weight in air, that is, or the mass in air, or up to what it is in air minus what it is when you put it inside liquid. Because you know that in liquid everything tends to have lesser weight. The same way that when something is going up the sky, it tends to have more weight. So weight of air minus weight of liquid is equals to weight of liquid displaced. So let's say weight of air is the initial weight minus weight of liquid L equals to weight of liquid displaced. And this weight of liquid displaced can also be called loss of liquid, or you say equal volume of liquid or solid, equal volume of liquid to solid. Let's do it this way, to solid. So whichever one you want to put it as. So another way to look at this, everything here is what you call upthrust equals to weight of liquid displaced. And you need to know that this is also the same thing as mg equals to, this can be the same thing as pgv. If you remember, inside that liquid as it has entered, so you can say this one can also be considered as weight of water equals to weight of liquid. This cannot, yes, or this can also be considered however you want to put it. There are so many ways you can think about this. This one that you have here is simply gotten from density equals to mass over volume. And you know that mass is the same thing as saying PV. And since this thing here is force is equals to mg. So if you come and put m is this density and v, then the g that is here. So a different way. But let's complete the question. They said in that question that we should use it to derive an expression. Okay, let me make room for that. Let's, so that we can answer the last question. They said derive an expression for the force experienced by an object of weight and density of weight and density. Okay, the body of weight, this is mg, and you have p naught. And you know that m from density, this is m over v. M is equals to density v. So you know, but let's be watching. And density, when it is fully immersed in a liquid of density. So so force experienced by an object of weight and density when it is. So let's say I have, first of all, what is the relation between, first of all, Archimedes principle is like this: W equals to so when it is totally immersed in a liquid of density, so P then G and V. That means that if I have this now, this should be mg p naught. Okay, but this can be Archimedes principle. Yes, okay. So well, from here, yes, if it's having density, no problem. So I can come here and just say that this is the sentinel saying replace this m. This m is having initial here, so it's going to be the sentinel saying p naught gv is equals to p g v. So this is also valid. This is also valid. So there are different formulas you can derive from this. So many. And you know that if that be the case, this can always cancel this. So you just have okay. Let's answer the next question. They said a solid object or a solid weighs 237.5 gram in air and 12.5 gram when totally immersed in a liquid of specific gravity 0.9. Calculate the relative density of the fluid. That thing they said fluid is supposed to be relative density of the solid. You know that sometimes that your textbook will be speaking English that puts people in trouble. So it's supposed to be relative density of solid. And you need to know that anytime you are talking about relative density is not complete unless you are comparing that into water. Relative density in simple terms is simply how heavy a substance, a liquid or a solid is compared to water. And why is it being compared to water? Because water in gram is simply 1 gram, and one of anything is more like a unit. So in kilogram is 1000 kilogram per meter cube. In gram is 1 gram per centimeter cube. So every object, every liquid is almost, especially every liquid is or every solid, you compare it to water. While in air, every gas is compared to air. So you're at 4 degrees centigrade, you need to know that. So or Celsius. So if I know this, so I will simply say this solid I'm given, the mass in air. Notice I'm always using the gram. I'm not trying to convert it to kilogram because this relative density and uh, Archimedes principle, we always trying to use that gram because one, the reason for comparing to water is because water gives us one. If I take it to kilogram, is 1000, which is the same as 1 in gram per centimeter cube. So we normally, when we get this course, we normally keep it in the gram. No need trying to do that. We are converting. But if you want to convert, no problem. So a solid weighs mass 237.5 gram in air. So let me put MA for air, mass in air. Then when totally immersed in water, something will have to drop. It feels lighter. So mass in water is 12.5 gram. Now, in a liquid. Now, the liquid has a specific gravity, which is relative density. I've told you that another name for before it used to be the same way you call length pounds, the unit of length pounds. Before, unit of how they address relative density used to be specific gravity. So relative density of the liquid. That's why you normally see in some textbook, if they want to represent relative density, they use one small sign of S. So 0.9 for the liquid. They're now asking us to calculate the relative density of the solid. Because that's what I don't know. If that book, you now see where they said of the fluid, you will be confused. So it's of the solid. So the idea here is to remember first what upthrust is. According to Archimedes, upthrust equals to weight of liquid displaced. So it's more like whatever, yes, there's a liquid I'm giving, But in order to find the relative density of that solid, I have to compare it to water after everything. So first I will say upthrust. So weight in air of that solid 2, that is 37.5 minus 12.5 is equals to weight of liquid displaced. So is equals to loss of liquid. Weight of liquid displaced is equals to loss of liquid. So the loss in the liquid is 237.12.5. 237.5 minus 12.5. So 225 is equals to weight of liquid displaced, which is what we call loss of liquid. This topic is one kind trick because it's just something they pull out question from every angle and you might get confused. So first of all, I now fall back. I've gotten the loss in liquid, but they gave me relative density. Let me use it. So relative density, if you remember, is equals to a lot of things. Relative density can mean loss of liquid over loss of water. It can mean weight in air over loss in water. It can mean upthrust of solid or upthrust of liquid, which is the same as loss of liquid over loss of water. So whichever one, it can mean density over, it can mean density of substance or solid over density of water. It can mean so many things, mass of. So it's just the reason why you have to pay key attention to the question. So I'll now say loss of water here, loss of liquid here, I know it to be 225. Then the relative density of that liquid, because if I have liquid on the numerator, which means I'm talking about relative density of the liquid, is 0.9 given. But loss of water, do I know it? No. So loss of water, I don't know it. So to get the loss of water, you always have to compare to water. So since they asked me relative density of the solid, I'm trying to make room for me to compare the relative density with water, with loss. So with what I have from water. So loss of water will simply be, it will come and go here, become coefficient, then divided by the coefficient. So 225 divided by 0.9. So 225 divided by 0.9. So the answer there for loss of water is 250. So 250. And notice that this is going to be in gram. Yes, because notice that this one that I have here is in gram. So this is going to be in gram, loss of water in gram, the amount of water lost in gram. So if I know this, to find the relative density of the solid now will simply be relative density of solid will be equals to loss of solid. But so I don't have anything. Another name for this loss of liquid is the same thing as saying upthrust of liquid over upthrust of water. So if I know this, so relative density can also mean mass in air or mass of solids all over upthrust or loss in water. So that means that if I want to get this, it will now be relative density of solids. To get it will now be mass of solid in air is 237.5. All of upthrust of liquid or loss in water, of upthrust of water or loss in water is simply 250. So if I do 237.5 divided by 250 to give me 0.95, and that's the answer. And you know that this relative density has no unit. So that's the answer. Why does it not have the units? This is in gram, this is in gram. Cancel, cancel. So you know that. So okay, this is an example. In our next class, I'll be treating examples. So the textbook examples that they solved there, I don't like how they solved it, so we'll be resolving it. Subscribe to my channel. Thank you.